Hello, welcome to a new video. In this video, we're going to talk about disaggregated prefill and decode. So in the last video, we talked about kind of single node, right? You can do chunk prefill, ragged batching, continuous batching. But this has a few problems. So the first is that when you have a single node and you're doing both prefill and decode, it's hard to tune the GPU for both simultaneously. One is compute bound, one is memory bound. So it's hard to tune the block size, the SM occupancy, etc. The second is latency interference. So the basic idea is if you have a batch and you're doing continuous batching, your prefill is either going to be waiting on the decode, or more likely your decode is going to be waiting on the prefill. And so you basically have this like long pull problem where you're kind of waiting longer to finish a request than you need to be. There's also this problem of KV cache memory contention, where remember like the decode step is memory bound. It's kind of waiting on transferring the KV cache and the weights to the compute units. And so one way that you can amortize this cost is by having larger and larger batch sizes. But this is actually in contention with prefill, which likes to create new large KV cache blocks. And then lastly, there's some like cache thrashing, where prefill reads tokens sequentially, whereas decode does random reads, and mixing them thrashes the L2 cache. So a lot of the following slides are from this distserv talk by the HAL lab. I'm just going to go over it because I think it's a good motivation for the reason you want to do disaggregated disaggregated prefill and decode. So to motivate it, let's think about like high-level system metrics. And the basic idea is that when you're doing LLM serving, there's actually two things you care about. So the first one is time to first token, and this is basically the latency from sending a prompt to getting a response. But then you have this second thing, which is TPOT, which is time per output token, where you basically want to reduce the amount of time it takes to generate new tokens. And here they have these like graphics that illustrate this idea of good put and throughput, where you can have really high throughput, but if the latency is high, then you don't have a good experience. And so they're trying to draw this idea of like good put. So like you have like 200 millisecond budget for prefill and 50 millisecond budget for decode, and if you go past this, it's like bad. It's like bad put. Okay, and this kind of motivates a lot of the system design. So like in the first era of LLMs, it was all about reducing costs. So people just cared about throughput, and they're drawing attention to this idea that you care about latency as well. And like we were saying about interference, like what is the core problem? The core problem is if you're going to continuously batch these things together, you're going to run into a problem where either the prefill takes longer than the decode, in which case this decode just has this like wasted latency. It could have done this next token, but instead it has to wait for this prefill to finish, or the prefill has to wait for the decode to finish. And so you basically have this interference, whereas if you have it on separate GPUs, then there's no interference. Furthermore, they call attention to this idea that you can have parallelism for speeding up operations. I'm not going to go into too much detail here, but let me just call out TP and DP. So what is TP? TP is the basic idea that imagine you have a really big matrix. Instead of doing that entire matrix multiplication on a single GPU, you can shard the matrix multiplication across multiple GPUs. And because you're using multiple GPUs and you have more SMs and more compute, you can do that matrix multiplication faster. And so this is really good for prefill, right? Because prefill, we're doing a lot of large matrix multiplications. In contrast, for something like data parallelism, prefill is completely compute bound. So there's no value in doing data parallelism. But for decode, it's actually quite valuable because then it means that you can do more decodes simultaneously. And PP, it also favors decode, but we're not going to go into that. And the basic idea is like, if you have a single GPU doing both prefill and decode, then you cannot apply both parallelisms. You have to apply one trading off the other. However, if you have some nodes that are doing prefill and some nodes that are doing decode, then you can apply TP on the prefill and DP on the decode, and you get kind of the best of both worlds. So their whole solution is like disaggregation. So you have some prefill workers, some decode workers, and you apply what we discussed above. They have some really interesting empirical results where if you have a single GPU that's doing both, then you get a 1.6 request per second good put. However, if you disaggregate across 3 GPUs, 2 GPUs for prefill, 1 for decode, and then you normalize it by the number of GPUs, you're actually getting 2x the good put for the reasons we talked about above. And then in practice, the way you implement it is you kind of have these clusters of prefill and decode. The prefill is calculating the KV cache. It's doing a transfer to the decode, and then decode can continue doing decode with the calculated KV cache from prefill. Okay, so hopefully that was useful. Yeah, I will see you in the next one.